In chapter 3, we're going to go into functional groups. Some of these functional groups we've been talking about this semester. We may have seen them in previous chemistry classes, but this is now an expectation that you're really able to start to name and understand what these functional groups are. So in organic chemistry, we always start with a carbon-based backbone. So hydrogen carbon is typically the backbone on which our functional groups will attach. So they're typically going to be non-hydrocarbon groups. And here's an example of a hydroxy group. And then that turns this from an ethane into an ethanol. And we're going to talk about those backbone groups and how those naming systems occur. But you can see here that we've adjusted the ending because that carbon area is the same length. So it's an eth group. And then we add the OL ending for the hydroxyl group, or the hydroxy group. So this is the beginning of one of the functional groups. So you'll see this common pattern where we'll have this carbon skeleton, and typically we'll refer to that as an R group. And you might have R group, R primed, R double primed, and that just tells us that there might be one or more different carbon skeletons attached to our functional group. Some of the things that you'll notice with functional groups is there is going to be a change in electronegativity most of the times between the carbon and the thing that's attached. So it's an important thing to recognize and to point out, because that hopefully will draw your eye to the functional group. Recognize that's a lot of the time where the chemistry is going to happen. So here, for instance, if we have an oxygen attached to carbon, oxygen is more electronegative. We give it a partial negative charge, that carbon gets a partial positive, and then we might know if this is going to act as a nucleophile or an electrophile for the chemical reaction that we're interested in. So again, here we have the oxygen can be a nucleophile because it's negatively charged partially and it has lone pairs, and then it would be an electrophile for the carbon because it is deficient in electrons. Something else that I want to point out, this term heteroatoms, atoms other than carbon or hydrogen. So that is what is most of the time going to be part of our functional group. That's heteroatoms. However, at times we also consider double bonds, which a lot of times will be between carbon-carbons or triple bonds. Pi bonds are easily broken. They can be used as a base and a nucleophile source. So these double bonds also are considered functional groups, even though they're not heteroatoms. As I mentioned in the last slide, these functional groups really is in a response to the electronegativity differences set up between the carbon and the heteroatoms. So the chlorine, for example, is more electronegative. It'll draw out negative charge from that carbon and make this partially positive carbon. Here we have base nucleophiles, pi bonds that are easily used in chemical reactions as the nucleophiles. Delta partial positive on this carbon because the oxygen is more electronegative. We have another base and then more pi bonds. So just examples of how these all can be the centers for chemical reactivity in other reactions. And again, like I said, we build in organic chemistry on these ideas, and now we're just going to expand these out. We've already been practicing some of the aeroformalism, but we can see here this alkene, and we'll talk about that naming of that compound. But we have these double bonds going towards the electrophile or the partially positively charged component. And where a nucleophile, remember, we go away from those electrons and point to where they're going to attach. So here are just some examples of that chemistry and where those electron affinity differences are set up in these functional groups. So when you're watching these videos, I want you to have a piece of paper out or somewhere to write down these notes and work on these problems. This learning check, again, these should all be in your notes, and you should be able to have these pictures if you're not very fast at drawing these out. It might be helpful to just draw on this slide. But what I'd like you to do is I'd like you to label the electrophilic and nucleophilic sites. So notice there's sites, so multiple sites on these molecules. And then we'll talk about this in class. So we'll start this. So I'm not going to give you that much time to do this in class because I want you to do this while you're watching this video. So pause here, finish this, and bring your notes regarding this to class. The first functional groups I'm going to go over are just the hydrocarbons. So not the heteroatom components, just when we're only talking about carbon and hydrogen, so hydrocarbons. The alkane is the first kind of compound, and the general structure is this R group and a hydrogen attached. Just means that we have carbons that are saturated with hydrogen along the chain. And it's not really technically a functional group. It's really the backbone of the organic compound. Alkenes, notice the alkane, and then we change the ending to an ENE ending instead of an ANE ending. So that little subtle difference, that tells us that we have a double bond in our structure. So we have a general structure of carbon, double bonded carbon, and you can see this trigonal planar orientation and shape. And that is an example here where we're just showing you all of the hydrogens. And the functional group is really this double bond here. And we know that it happens because of the name ENE ending. That tells us it's an alkene. Now you'll notice alkane, alkene, alkyne. YNE ending tells us there's a triple bond. And it's the same idea that we look for the double bond, except for we've added another bond on there. Remember, these are sp3 hybridized. We have to unhybridize one of those p orbitals to sp2 for the double bond, and then this is sp hybridized. So that's the difference between those in terms of their hybridization state. We go from tetrahedral, trigonal planar to linear for between these carbons. And then we have aromatic compounds, and this is called a phenyl group, and you can see that alternating double bonds here. And we'll talk about the importance and how that works and why that's a special scenario and how to determine what an aromatic compound is. But right now, just notice that we have kind of these alternating double bonds between carbons. So remember, carbon, 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 carbon. You'll notice each carbon has a double bond attachment, but we don't have them between all of the carbons. If we did that, there would be too many bonded bonds and we wouldn't have any hydrogen. So this we'll talk about this special case and what it's doing. Before we get into aromatics, I want to talk about the classification of typical alkanes. And one of the things that we need to do is we look at the chain length. And you'll notice that we have different groups along chains, and we'll have different types of carbon. So we'll be I'll talk to you about a certain type of carbon, and that might dictate the type of chemistry that's happening on that carbon. If we're looking at a primary carbon, for example, this carbon in the blue, if it's attached to just one other carbon, that's telling us it's a primary carbon. So these are not attached to other carbons at the end. Maybe they're different functional groups or hydrogens. We're not defining what these things are attached to, but this is attached to one other carbon. That makes it a primary carbon. If we have a 2 carbon attachments, that's a secondary. If we have 3, it's a tertiary carbon, and then 4, it's a quaternary carbon. So that is how we would define different types of carbons. And there's going to be important to be able to recognize these, because that might change the chemistry, the acidity of that, or the basicity of that carbon. It'll change some of the chemical characteristics of those areas, how nucleophilic or electrophilic that might be, for example. On one chain here, we can see carbon, 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 right? This is a chain of carbons. And here, unlike these are actually carbons at all of the ends. This one, here we can see this is an example of a primary carbon, because I can count to 1 carbon attachment. Here we can see, I like to draw an arrow towards the carbon. So that's primary, because we just have 1 attachment. If we go to the second carbon in blue, we can draw an arrow to 1 carbon and an arrow to a second carbon. So that's why we have a secondary carbon. Here, tertiary, we can draw 1, 2 carbons, 3 carbons, and then the quaternary, the same 1, 2, 3, 4 carbons. So that's just some naming of carbons that you'll be expected to be able to do and to recognize. The other thing that we'll do is to classify the hydrogens on attached carbons. So if we are talking about this carbon here, and we are talking about that hydrogen that's associated with the carbon, it is attached to a carbon that's attached to 1 carbon. That means this is a primary hydrogen. This carbon here is attached to 2 carbons. So this becomes a secondary hydrogen. This carbon is attached to 3 carbons. That's a tertiary. So notice the hydrogen is the primary, secondary, tertiary is based on the carbon that it's attached to, not itself. So we can't then have a quaternary carbon, we can have a quaternary carbon, but you'll notice that this one can't be attached to any hydrogens. So we can't have a quaternary hydrogen, for example. And this is just an example of more examples of where this carbon here is attached to this. This is just a primary hydrogen. Those are primary hydrogens because the carbon is attached to just one other carbon. In the middle here, this carbon is attached to 2 other carbons. So these hydrogens are secondary. And then here, this carbon, we have a carbon and a carbon and a carbon. It's attached to 3 carbons. So that's a tertiary hydrogen. And so we have primary, secondary, and tertiary hydrogens on those different carbons that are defined by the carbons they're attached to. So can we have quaternary hydrogens? Answer this question. I just mentioned it. If you didn't get that, go back, recognize why, and then we'll bring this answer to class. And then also I would like you to look at classifying all of the carbon atoms on these atoms, all of the carbons. So these are carbons on all of the ends and over here as well. And then also classify the hydrogen atoms that are attached. So you might have to redraw this or draw in the hydrogen atoms in there. How many primary, secondary, tertiary hydrogens are there? So that's answer those and then come to class and we'll chat about this when we next meet. This was just a short little video regarding the hydrocarbon section, and next we'll start getting into some of the more heteroatoms and the different functional groups that are made up of those.